Today I want to talk about intersections between three planes. We've already talked about intersections between two planes in a different video. So like this is one of the planes, this is a different one, and the intersection between the two planes is this line right here. Today we're going to find a way to put a third plane in this picture, something like this. And it will be interesting if you have watched the other video before, but I don't think it's exactly necessary. Over there, we have talked about a lot of intersections between two different things in three dimensions. So we had the intersection between two planes that I just mentioned, the intersection between a plane and a line, which is just one point. There's also intersections between two lines in three dimensions, which we're not going to need today, but it's an interesting situation because sometimes there isn't any intersection. The most important thing to know is that the intersection between two planes in the three-dimensional space is a line. And when you put the third plane into the picture and you want the intersection between all three planes together, you can think of this as you just did the intersection between two of them first, and then there is this line. Now you want the intersection of that line with the third plane, which is then going to be a point, right? Like the intersection between any line and a plane is just the point where they touch. Most of this video is going to be algebraic and we're doing calculations and solving systems of equations. I just want to show you the geometrical interpretation of these things first, okay? So when I say that in general, the intersection between a line and a plane is a point, is because there are exceptions to this rule. It doesn't really matter if the line is perpendicular to the plane or not. It still has one point as the intersection. The only exception is when the line is parallel to the plane. Now it can be like this or in any rotation here, but a line that is parallel to a plane doesn't have a point as an intersection. So when I told you that the intersection between three planes is a point, that also has exceptions because the third plane didn't have to be in the back here. If the third plane is in some way in between the two planes, now they all share the same line as an intersection. And it's also possible that the third plane is here, and now they don't have any points as intersection. So we are going to talk about all of these things algebraically, how to find the one point of intersection between three planes, which is the general situation. We're going to talk about how to detect when we are in the special cases, the case where the three planes don't have any intersection, and also the case where they have a line as an intersection instead of just one point. But before we do that, intersecting three things in three dimensions, I want to go back a little bit to intersecting two things in two dimensions. And I know that I lose a lot of you when I do this. You're going to click away from the video because you came here to talk about three-dimensional stuff. You're not interested in talking about the intersection between two lines in the plane. This is very easy. You learned this in middle school or whatever. But I do want to talk about this first because there is an analogy that I want to make in the three-dimensional case. And if you want to skip ahead, that's fine. Just don't go away. So I'm thinking about these lines in slope-intercept form, right? This is not the usual way in which we see systems of equations being written, but it's the same thing. We're talking about the same two lines. Now, when you learned this, probably in middle school, there's a good chance that you learned about two different methods. One of them involves some way of adding the two lines together or subtracting one line from the other, and the other one was called a method of substitution. For today's purposes, I'm going to argue that adding two lines together is far, far superior than any kind of substitution that you could think of doing. But if substitution is your favorite method, then I promise you that at the end of the video, I will talk about a completely different kind of situation in which it is way more appropriate. Okay, so for now, I'm going to solve this system, and it looks to me like the most obvious way to solve it would be to do one line minus the other, because then the y's would just cancel out. But I'm going to make a different choice instead. I chose to multiply the second line by 3 instead, and then subtract the lines, and then I'm canceling the 3x instead of canceling the y. The reason why I did that in this example was only to remind you that I can, that this is a possibility, that adding two lines together is a possibility. Multiplying a whole line by one number is also a possibility because I'm just doing the same operation to both sides of that equation. Other things that are possible are that I can switch the order of the lines. Obviously, this doesn't matter. They are simultaneous anyway. And I'm saying these things because they're the kind of things that I'm going to be using when we move back to 3 dimensions. But before we do that, I want to talk about the exceptions. This system of equations has one solution, which is that point where the two lines intersect. But in what kind of cases is the solution to the system not a single point? There are two different situations in which this happens. One is if the lines are parallel to each other and then they have no intersection. And the other one is the case where the two lines are actually the same line. I'm not sure if you can see there, but there's actually two colors. In this case, there are infinitely many intersections. All of the points of the lines are intersections. It's not just one. So most of the time, one intersection, sometimes either no intersection or infinitely many intersections. And both of the exceptional cases happen when the two lines have the same slope. And it's easy to identify in the system of equations when the two lines have the same slope. It's just that one line is going to be a multiple of the other. And now to distinguish between the two cases, the case with no intersections and the case with infinitely many intersections, you just have to check if the number on the other side of the equation is also doing the same thing. So here I've multiplied the first line by 2, and the right side of the equation was also multiplied by 2. And here the second equation is 2 times the first equation, but 7 is not 2 times 4. So in this case, we have no intersections, and in that case, we have infinitely many intersections. And in this case, even before solving the system, we already know that there's going to be one intersection because the two lines are not a multiple of each other. So that's easy to identify in the two-dimensional case. The problem with the planes is that the exceptional cases are not going to just be when one is a multiple of the other, because there's 3 of them. So there's more interesting things that can be happening. Of course, one plane being a multiple of the other is one of the possibilities. If 2 of them are parallel to each other, then it doesn't matter what the third one is doing. Already they have no intersection between the 3 of them. But the cases that I showed you before are different from that. Maybe these two have an intersection, and each one of them also has an intersection with the third one, but all taken together, they don't have any intersection. As well as the case where all 3 of them agree on the same line, and there's infinitely many solutions, which are all the points on this line. None of that is a case of one plane being a multiple of the other one, because there is no such thing as the other one. There's 2 other ones. So the equivalent concepts that we are looking for here is that the system is going to have exactly one solution if the 3 planes are linearly independent. This means that any one of them cannot be written as a linear combination of the others. And this is the thing that is equivalent to being a multiple of. In the two-dimensional case, a line needed to be a multiple of the other line. And here it doesn't have to be exactly a multiple of. It has to be only a linear combination. So maybe one plane, say plane C. Maybe plane C is plane A plus plane B. Or maybe plane C is 2 plane A plus 3 plane B. That's what a linear combination of things is. You get to multiply each one of them by a number and then add them together. That makes a linear combination. And if that is not happening between your 3 planes, none of them can be written as linear combination of the other 2. That means that they are linearly independent. And this is the basic case, what mostly happens most of the time. All 3 planes are linearly independent, and they just have one point of intersection. You're going to be able to tell that by looking at the normal vectors of the planes, because that is what's going to go into the system of equations that you want to solve to find their point of intersection. Because the Cartesian form of the equations of the plane are showing the coordinates of the normal vector right here. 2, 1, and minus 1, 1, 3, and 0, 3, minus 2, and 1 in this example. But unlike the case of lines, where it's pretty easy to see when one is a multiple of the other or not, here we look at 3 equations of 3 planes and we have no idea if one is a linear combination of the other ones, because there's so many things to try. It can be 2 of one plus 3 of the other, or a 7 of one minus 3 of the other. There's literally infinitely many ways in which this could be happening, so it's not a thing that you're gonna just look at it and see. It's going to have to come from the process of solving the system. But at least visually here we can understand it in terms of normal vectors, because both of the exceptional cases that I showed you, the third normal vector is going to be in the same plane as these other two. In this case here, where the third plane is in between the other ones, its normal vector is also in between the other two normal vectors, and it can be found as a linear combination of them. And the other case is the same, because the third plane doesn't pass through the same line here, but it also has a normal vector that can be built as a linear combination of this vector and this vector. Okay, so now let's talk about how to solve the system of equations. And of course, you could use whatever technique makes sense, okay? You can add lines to other lines, you can multiply lines by numbers, you can even use substitution if you want. All of that is correct and has a chance to work, but what I want to show you is that there is one way to do it that is better than all the other ways, and that is to be systematic about it. We are not going to use substitution at all. It is just going to be a sequence of adding lines to other lines in order to eliminate variables from each line in a very specific order. Not that other orders would be incorrect, but it's just that if you always do it in the exact same way, then it becomes a process and there is much less opportunity for you to make mistakes. Okay, so the first thing I'm going to do in this case is that I want to change the order of the first and the second line. The reason why I want to do that is because this x here is multiplied by 1 and the other ones are multiplied by other numbers. So it is going to make it slightly more simple to subtract this line from the other lines than the other way around. So I'm going to put this one here and this one over here. Okay, so I told you that this process is going to be systematic. You are going to eliminate the variables always in the same order. And the order is the following. First, you want to get rid of this guy, then this one, and finally this one, okay? But we're going to do them one at a time. So how to get rid of this guy is that I want to subtract 2 of the x's that are in the first line, because then you're going to have 2x minus 2x. That's going to cancel out and be 0. Of course, I can't just do that on its own. I have to take the whole line and I have to do minus 2 times the first line. As I do that, I am not going to change anything at all in the first line and the third line. So that's just a copy of them. And now let's see what's happening to the second line. 2x minus 2x is 0, and that was intentional. Now, y minus 2 of these is y minus 6y, which is minus 5y. And minus z minus 2 of nothing is just nothing, so minus z stays here. And the other side of the equation is also doing the same thing. So 2 minus 2 times 7 is 2 minus 14, which is negative 12. Okay, so that was the first of the 3 zeros that we wanted to make. Now we are going to go ahead and do this one. And we're going to use the same exact technique, except this time is 3 instead of 2. So we're going to take the third line and subtract from that 3 times the first line. We're doing that intentionally so that that 3x is going to disappear. But while we're doing that, we are not going to change anything at all in the first 2 lines. So here's a copy of them. And now let's see what is happening to the third line. Well, 3x minus 3 of these is 0, like we intentionally wanted it to be. Minus 2y minus 3 of these is minus 2y minus 9y. So that in total is minus 11y, because we're doing the entire line, okay? So it's this minus 3 of this, and then this minus 3 of this. Now this z minus 3 of nothing is just z, and 6 minus 21 is negative 15. That is 2/3 of the way done. This process is not very difficult at all. The only thing that you have to keep in mind here to do it always in the same exact way is that in order to make this 0, you were looking at this x here. And in order to make this 0, you were also looking at that x. But now that we want to go for the third 0, we want to find a 0 here, you are no longer going to be able to use the first line for that. That's not going to work. Because if you were to subtract some amount of the first line in here in order to make this a 0, you would also have to put some of this x into that one that is already a 0. So you would be making one of the zeros that you want while simultaneously destroying the other. So we don't want to do that. So instead, in order to make this 11y into a 0, we are going to look at the second line. We're going to add or subtract some amount of that line, because when we do that, the 0 that we already have here on the line is not going to get destroyed. It's going to be subtracting or adding something that is itself already also a 0. So it's not going to matter. It's not going to break the zeros that we already have. Well, this time I am not getting a pretty number, okay? I did not choose the numbers for this example intentionally so that the numbers would be pretty. So I was lucky so far, but now I have to multiply by 11/5. Whatever. In any case, as I'm doing that, I am not going to change the first or the second line. So let me make a copy. Now let's go. 0 minus 11/5 of 0 is just 0. Minus 11y minus 11/5 of minus 5y is actually 0, and that was done intentionally, okay? That's what the number 11/5 is doing here. That was intentional because I want this to be a 0. And now let's just see what happens here. Z plus, because minus with minus, so z plus 11/5 of another z is 16z over 5. And the same thing needs to happen to the numbers here. Minus 15 plus 11/5 of 12. Here the minus with minus is plus is also happening. So that's an ugly number, 57/5, but it doesn't matter that it's ugly. It's the number that goes here. And at this point, the problem is basically over. We got the 3 zeros that we were looking for, one after the other in the same order, as we're always going to do that. And now the second part of the process is that we're going to start reading these lines from the bottom to the top. So the last line is telling me that 16z over 5 is equal to 57/5. Well, the numbers are ugly, but at least they're in the same denominator. So z is equal to 57/16 is already part of the answer that I was looking for. This is the z coordinate of the point that is the solution to the system of equations. And what I need to do now is to keep bringing that up to the next line. You see, the next line is telling me that minus 5y minus z equals minus 12. So, well, 5y plus z is 12. 5y is 12 minus z, but I already know z is 57/16. So again, a little bit more annoying calculations with fractions, but we get that y is equal to 7/16. And I am 2/3 of the way down to the answer of the problem, because now I have the z coordinate and the y coordinate of the point that is the intersection between the three planes. Now, lucky for me, the first line that I still need to look at doesn't have any z. That's because it originally had a 0z over there. So I only have to write down x plus 3y equals 7, but I already know y. X is equal to 7 minus 21/16. And if there was a z in this line, you would just subtract it with the value of z, because you already have that as well. So that's it, basically. This is the method. The only other thing that I have to show you is that it can take a little less time to do this if you're writing fewer things. So let me clean up this screen a little bit and then write it all again, but with fewer things that I have to write so that I can do it faster. Okay, so from the top, I had that 1 in front of the x. There are a bunch of other 1s here, and there is also a 0 right here. So the thing that I am going to do now is that instead of writing those three equations, I am going to write just the coefficients. So 1, 3, 0, and then 7. 1, 3, 0, and then 7. On the second line, the list of numbers is 2, 1, minus 1, and 2. So 2, 1, minus 1, and 2. And then 3 minus 2, 1, 6. 3 minus 2, 1, 6. This is just a shorter way to write down the system of equations without having to write down all of the x's and y's and z's, because you are in agreement with yourself that they are always going to appear in the same order. So the first number refers to x, the second one is to y, and then the third one is z. You don't have to keep writing them over and over again every single time if they're just going to be doing the same thing in the same place. But now you already know that you want to subtract 2 of the first line into the second line. That is because 2 minus 2 ones is 0, and you want to make this into a 0. So when you go for the second step of the process, you are not going to do any changes to the first or third lines. You are just going to subtract 2 of the first one into the second one. So 2 minus 2 ones is 0. 1 minus 2 threes, which is 1 minus 6, is minus 5. Minus 1 minus 0 is just minus 1. And 2 minus 2 sevens is 2 minus 14, which is negative 12. And if you notice, 0, negative 5, negative 1, and negative 12 are exactly the same numbers as we had here, because we are doing the same thing. We are just writing less. So now we are going to do the same thing again to the third line, subtract 3 of the first line into the second line. Let's make a copy of the first 2 lines because we are not going to change them right now. 3 minus 3 ones is 0. Minus 2 minus 9 is minus 11. 1 minus 3 zeros is 1. And 6 minus 21 is negative 15. Again, because the process is the same, here are the same numbers again. 0, negative 11, 1, and negative 15 are exactly the same numbers as we have here. And finally, you do the same thing with the 11 over 5, right? I don't have to go through the fractions calculations again because I've already done that. But the point is to subtract 11 fifths of the second line into the third line. This does nothing to the first number here because it's 0 minus 0. The second number is going to turn into a 0 because I'm doing this intentionally. And the third one is 1 plus 11 fifths because it's 1 minus 1 times minus 11 fifths. And that gives us 16 over 5 just like before. And then you do the same thing to the numbers on the right, and we already know that the answer is 57 over 5. Then you're going to go through that backwards process again. You know that what this line here reads is exactly this. So you're going to do z is equal to 57 over 5 divided by 16 over 5, which is exactly what we did before. Find the number of z, plug it into the previous line, and then both of them into the first line to find the value of x. Now, one of the things that we spent a lot of time talking about in the first part of this video were the special cases where you were not going to find just one point as a solution like we found here. This was one point with coordinates x, y, and z. But we talked about all of those different cases, the cases with no solutions, the cases with infinitely many solutions, and how to detect them while doing this process algebraically. The thing is that sometimes when you get to the last line, you have a 0, those were intentional. But sometimes, unintentionally, you're also going to get a 0 here. So you're going to find an equation that is just 0 plus 0 plus 0 equals something. And then at that point, there are two possibilities. Your line is either saying 0 plus 0 plus 0 is equal to 0, which is correct, and therefore implies that your system has an infinite number of solutions, or you are going to have a line that says 0 plus 0 plus 0 equals to a number that is not 0. And this is impossible. This is the situation that implies that your system actually does not have any solutions. Now I'm going to show you an example of this happening in an exam question. So he gives us the equations of three planes and says that the three planes intersect in a line. So it's like this case out of the cases that I was showing you before. One plane is a linear combination of the others, and they all intersect in this line here. There are infinitely many solutions to the system. The way we're going to make that happen in the question is because we have some freedom here. We want to find the value of b and d, which are unknown coefficients in the system. So let's begin by rewriting the system in the short way so that we can solve it faster. The first line has coefficients 1, 1, minus 1, and minus 2. The second one is 2b minus 1 and 3. And the third one is 1 minus 1, 2d. Remember that we have to make three zeros appear here in this order. First this one, then this one, and then this one. So in order to make the first zero appear, we are going to subtract 2 times the first line from the second line. So the first line has a 1, 1, minus 1. Subtracting 2 of that is minus 2, and plus 2. Well, and plus 4 here on the other side. So 2 minus 2 is 0. This is going to just stay as b minus 2. And minus 1 plus 2 is 1. On the right-hand side, we have 3 plus 4 is 7. And now we have to do the second 0 here. This is a 1, so I'm just going to subtract the first line from the third line. It's going to have a minus 1 here, minus 1. Here is a plus 1 because it's minus this minus 1. And here I'm going to have d plus 2. So 1 minus 1 is 0 as intended. Minus 1 is minus 2. 2 plus 1 is 3. And d plus 2 is just d plus 2. Now the third and final 0 that I have to make is this position here. And I told you before that I am not allowed to use the first line for that because then I would be breaking this 0 by subtracting part of this one here. So instead I'm going to make the 0 appear by using this line here. But this is going to potentially be a little bit more confusing because I don't have a specific number in there. I have b minus 2. Remember that I think that I want to make a 0 is the minus 2 that is already there minus some amount of the b minus 2. And if you think about it for 2 seconds, you realize that this is the factor that we want. But we have to do the same to the 3. So I have to take the 3 and subtract that same amount, but not of b minus 2, of this 1. So this is just times 1 here. So this is what's going to happen to this position here in the system after I do the subtraction. And the key here is that I want the three planes to intersect in a line. I want this to be the special case, not the generic case where there is one solution, which is one point. So in order for that to happen, it has to be that this turns out to unintentionally also be 0. Well, in this case, it was done intentionally, but you know what I meant. So yeah, 3 equals 2 over 2 minus b, and then 6 minus 3b is 2, 3b is 4, and b is 4/3. This means that the lines were not linearly independent. One of them can be written as a linear combination of the other two, but that doesn't say still that the three planes intersect in a line. This might also have been the impossible case, where the three planes don't have any intersection between all of them. To distinguish between those two cases, we need to make sure that the right side of the equation also unintentionally becomes a 0, because then the third line will be reading 0 plus 0 plus 0 equals 0, which is correct, so it implies infinitely many solutions. And it's the same thing, right? We're subtracting a bunch of the 7 here. So the d plus 2 minus 2 over 2 minus b, which was that factor that we found before, times 7, this also needs to be equal to 0 to get it to the case where there are infinitely many intersections. The value of b here we already know is 4 over 3. And now it's just a calculation. You find that d is equal to 19.